Hello, wonderful people. Here we are, section 3. We're going to talk about generators and alternating current. How does a generator make alternating current? Very cool. Whereas a motor converts electrical energy into mechanical energy, a generator converts mechanical energy into electrical energy. And yes, you can use the exact same piece of equipment for going both ways. It's just a coil inside of a magnetic field. And if you put electricity into it, you'll spin the coil. And if you take the coil and attach it to the Hoover Dam and use the water to spin the coil, then you get electricity out. A current can be generated by plunging a magnet into and out of a coil of wire. As the magnet enters, the magnetic field strength inside the coil increases, and induced voltage in the coil is directed one way. As it leaves, the current is induced in the opposite direction. Greater frequency of field changes induces greater voltage. So if you go back and forth faster, you get more voltage. The frequency of the alternating current is the frequency of the changing magnetic field within the loop. So the frequency of the alternating voltage, how fast it's going up and down, is the frequency of the changing magnetic field within the loop. All right, this is going to get easier with pictures. In the real world, it is more practical to move the coil instead of moving the magnet by rotating the coil in a stationary magnetic field. A machine that produces electric current by rotating a coil within a stationary magnetic field is called a generator. A generator is essentially the opposite of a motor, converting mechanical energy into electrical energy. So there's the arm doing the work of pushing that in a circle. And there's the coil. And as that coil cuts across the magnetic field, which is going straight up and down, as it cuts through the most lines, you get the most voltage. And then it comes out here and goes to the light bulb. We've used this picture before. All right, starting perpendicular to the field, the loop has the largest number of lines inside. And as it rotates, the loop encircles fewer of the field lines, less flux, until it lies along the field lines when it encloses none at all, no field line, no magnetic flux lines. As rotation continues, it encloses more field lines, reaching a maximum when it has made a half revolution. The magnetic field inside the loop changes in cyclic fashion. So let's look at the pictures. I think these are much more helpful. So all those sentences are over here. So here we have the north magnet and the south pole magnet. So the field lines are going straight across. And if you look at the coil, it encloses all those field lines. That's what he used the cross hatching to represent. A lot of field lines in there. And as you rotate it, the top is coming down, there's fewer field lines. So that top piece of wire is cutting across a bunch of field lines as it comes down. And then when it's completely across, there's no field lines going through it. So with no field lines going through it, for that brief instant, there is no voltage produced in the coil. I'm sorry, I just made a mistake. I'm going to have to cut that out later. Right. When this, all right, for letter C, the piece of wire here is cutting down through the most field lines. This wire is cutting across the most field lines. When the wire's up here, it's cutting across few field lines. So when it's cutting across a bunch of field lines going across here, that's when it's producing its maximum voltage. And now it comes down again, and it starts to enclose more field lines again, and it's going to come all the way across to right here where it's moving parallel to the field lines. So it encircles a lot of field lines in it but this is moving parallel to the field line. So this is the effective area within the loop at different rotational angles. So as that cross area changes, so does the voltage produced. So when the when it's up here like this, that's producing 0 volts. And as this comes down, then it's doing its maximum voltage right there. Then here, it's back up again, and it's at 0. And here it's at its maximum voltage, but since it's going in the opposite direction, now the voltage is in the opposite direction. So here it's a positive voltage. And then finally, it opens back up again all the way, so it's at 0 voltage. So it starts here, it goes down for a bunch of voltage, then up for a bunch of voltage, and ends here. And it's in the same position. And please note, in this position, the coil is upside down. I wish they'd labeled one end A and one end B, because this is the top, and then it's on bottom, and then it's on top again. This is from here to here is only doing half of one complete turn. You see that? The voltage induced by the generator alternates, and the current produced is alternating current, AC. The current changes magnitude and direction periodically. The standard AC in North America changes magnitude and direction during 60 complete cycles per second, 60 hertz. Now, complex generators. Generators used in power plants are much more complex than the model discussed here. Huge coils make up many loops of wire, and they are wrapped on an iron core to make an armature much like the armature of a motor. They rotate in the very strong magnetic fields of powerful electromagnets. And that's what I used to do for a living. So here's what it looks like in a cartoon picture. You have, do you know those pinwheels the little kids play with? You blow on them and they spin. It's just a fan, right? Well, this is just a fan. The difference is instead of blowing air from out of your mouth, we use steam where we boil lots and lots of water, and we use steam to come across the fan, and that makes the fan spin. Then that spinning fan we hook up to the generator, which is the coils of wire are wrapped around the magnet, and then this rotates around like that. So these coils are going around and around, and those coils are what gets the voltage coming out over here. And this voltage is made because this big magnet is stationary, and it always has the north field going down, and that's the field lines that these are crossing. And that's the name for the part in there that spins, the armature. The armature is connected externally to an assembly of paddle wheels called a turbine. That's called a turbine. While wind or falling water can be used to produce rotation of the turbine, most commercial generators are driven by moving steam. True. At the present time, a fossil fuel or nuclear fuel is used as the energy source for the steam. Yes. An energy source of some kind is required to operate a generator. Some fraction of energy from the source is converted to mechanical energy to drive the turbine. The generator then converts most of this mechanical energy into electrical energy. Now, some people think that electricity is a source of energy. It's not. It's a form of energy, and this must have a separate source. So the separate source ultimately is oil or coal or gas or uranium for nuclear power, or wind if it's a wind generator, or falling water from behind a dam. All right. How is a generator different from a motor? You should be able to answer that. If you can't, then go back and check your notes and maybe rewatch this video.